Hello and welcome back. So in the last video we were talking about second order homogeneous linear equations and we were discussing about the characteristic equation. We will move forward from this, we will go ahead and talk about that a little bit more. So let's first recall what we covered. So the general form of second order homogeneous linear equation is given by ay double prime by prime plus cy equal to 0, and since we are considering constant coefficients, we'll say a, b and c are constant. So this is our general form. For finding out the solution for this equation, we talked about characteristic equation, and the characteristic equation is this coefficient a. Here we have y double prime, so we'll write r square plus b time, for the first derivative we will write r plus c equal to 0. This is our characteristic equation for this above ODE. So this we call characteristic equation, and this is very important equation to determine the solutions, because we saw that if r is a root of this equation, then e power rx is a solution to this ODE. So now this characteristic equation is quadratic. It means it have two roots. These two roots can be real and distinct, can be equal and can be complex, right? Okay. So whenever we are dealing with second order equation with constant coefficient, first step is to write the characteristic equation. Second step is to find out the roots. So the roots to this equation we can find out either by factorizing or by quadratic formula. And by quadratic formula we know the roots are going to be r1 r2 equal to minus b plus minus square root of b square minus 4ac divided by 2a, and the roots are real or complex depends on the sign of b square minus 4ac, right? If b square minus 4ac is positive, then r1 and r2 are real and distinct. If b square minus 4ac is 0, we will get two same roots. If b square minus 4ac is less than 0, we will get complex roots. And then we saw how to write the general solution in each case. In this video, we are going to see some examples to make things more clear. So let's start with the first case, when we have real and distinct roots. Probably I should write which example we are talking about. So we are dealing with the case real and distinct roots. Okay, so our first example is y double prime plus, or say minus, y double prime minus y prime minus 6y equal to 0. We want to solve this ODE. So our first step is to write the characteristic equation. If we have second derivative, we will replace it by r square, first derivative r, and minus 6 equal to 0. This is our characteristic equation. Characteristic equation. Now we will find out the roots of this equation. We can use either quadratic formula or we can factorize it. This equation looks simple, so I'm going to factorize this, and we can factor it r minus 3 times r plus 2 equal to 0. So the roots are either, so if the product is equal to 0, one of them is equal to 0. Either r minus 3 is equal to 0, which gives us the value 3, or r plus 2 is equal to 0, which gives us the value of r equal to negative 2. So r equal to 3 and r equal to negative 2 are two roots of this equation. And then we know how to write the general solution. So okay, first let's write down what will be the two independent solutions. So e power 3x and e power negative 2x, these two are linearly independent solutions of this ODE. And if you remember, we talked about it that number of linearly independent solutions are going to be equal to the order. Here order is 2, so we have two linearly independent solutions. Every other solution will be a linear combination of these two. So the general solution is given by y equal to c1 e power 3x plus c2 e power negative 2x. This is our general solution. Okay, like here yx is c1 e power r1x plus c2 e power r2x. Let's see one more example. So the next example, let's take an initial value problem. Solve the IVP. 4y double prime minus 8y prime plus 3y equal to 0, and y of 0 we want it to be 2, and y prime of 0 we want it to be half. Okay, let's solve this one. These are very easy. Okay, so let's first write down, the first step is always to write down the characteristic equation. Which is 4r square minus 8r plus 3 in this case, right? Now you can factorize or you can find out the root using the quadratic formula, right? Okay, so if we want to factorize, we know the product. So here I know you all of you know how to factorize, but I'm just giving you a recall. The product needs to be equal to a times c. This is your a, this is your c, which is 4 times 3 equal to 12, and the sum we want it to be coefficient of r b equal to negative 8. If the product is positive and the number is negative, it means the sum is negative. It means both of the number we want them to be negative. So what we do is we factorize this 12. So it can be 12 times 1 2 times 6, 3 times 4. Now if you write 4, it's going to repeat 4 times 3, then 6 times 2, and so on. Okay, so 4, 12 and 1, the sum is not going to be -8 in any case, so this doesn't work. 4 and 3 doesn't work because the sum can be maximum 7. But 6 and 2, if we take -6 and -2, the sum is going to be -8. So what we'll do is, we will write this equation as 4r square minus 6r minus 2r plus 3 equal to 0. And then from the first two term we can pull out 2r. So we will get 2r minus 3. From the second term we can pull out -1, because whatever in the parenthesis we want them to be the same. And then we can pull out 2r minus 3 times 2r minus 1 equal to 0. So all this we done for this step. So either 2r minus 3 is equal to 0 or 2r minus 1 is equal to 0. It means r is equal to 3/2 or r is equal to 1/2. We got two values of r. Okay, so our general solution will look like c1 e power 3/2 x plus c2 e power 1/2 x. This is our general solution. Any other solution will take this form only. Okay, but we had initial conditions also. Y of 0 is 2, so let's put the initial conditions. So y of 0 is 2. It means value of y is 2 when x is 0. So c1 plus c2 is 2. And the derivative, the second condition we have is the derivative at 0 is half. Here the derivative is equal to 3/2 c1 e power 3 over 2x plus 1/2 c2 e power 1/2 x. Okay, we plug in x equal to 0 and y prime equal to half. We get 3/2 c1 plus 1/2 c2, which is same as saying 3 c1 plus c2 is equal to 1. And our other condition was c1 plus c2 is equal to 2. We have these two conditions and we will find out c1 and c2 now. So if we subtract these two equations, we will get 3c1 minus c1 is 2c1, c2 will cancel out, equal to -1. So c1 is equal to -1/2. c1 plus c2 is equal to 2. So c1 plus c2 is equal to 2. So c2 is equal to 2 plus 1/2, which is 5 over 2. So our general solution which satisfy these two conditions is equal to c1 is -1/2 e power 3/2 x and c2 is 5 over 2 e power 1/2 x. So this is the solution which satisfies these two conditions and the differential equation. Okay, this was the case when we have real and distinct roots. What if the roots are repeated? If we get two roots which are same, that's our second case. Okay, now let's see one example for the case of repeated roots. Repeated, or we can also call it equal roots, when roots are equal. So consider the ODE y double prime minus 10y plus 25 equal to 0. We want to solve this ODE. So first step is always to write down characteristic equation. So the characteristic equation is r square minus, this is y prime and we have a y over here, sorry, 10r plus 25 equal to 0. We can easily factorize this equation as r minus 5 times r minus 5. You can also find the roots using the quadratic formula. So here the roots of the characteristic equation are 5 and 5. We have the repeated roots, right? So the general solution in this case is given by y equal to c1 plus c2x e power 5x. Okay, and if you want to write down what are the two linearly independent solutions, this is second order ODE, so we must have two linearly independent solution. In this case they are e power 5x and x times e power 5x. You can go ahead and verify that these two are linearly independent. Okay, we will stop here today and I'll see you in next video. In next video we are going to talk about when the roots are complex. Till then, practice some more problems about this and see ya. Bye bye.